Okay, shall we start? Shall we start? So we're and hang on, microphone. Wait yourselves. Hi. Okay. The microphone sometimes doesn't work, so if you're listening. I know you can do it. I know you can. Okay, so I don't want to teach today. I'm not feeling it. I don't know what it is. You don't want to be here either. So that means it's going to be a short lecture, and that's good. It'll also be, however, it's going to be a clear, concise, and perfectly done lecture, in which there'll be no issue whatsoever, and after this you will understand everything there is to understand about t-tests. No, that's not going to happen at all, but we're going to figure it out. So last time we started with the t-testing, which is not the sexiest topic, I know, but it is, because it's magical. For the first time now, you are armed with the ability to determine if the average something over here is different from the average something over there. And that's really what we're talking about with t-tests. Now, to be honest, professional statisticians and scientists have evolved beyond the t-tests, those the cutting edge of quantitative methods. Something called general linear models is becoming more and more common as a Bayesian method. But you don't need to know about that just yet. For the purposes of your undergraduate career, probably for most of your graduate career, and for many sort of non-heavily quantifiable quantitative professions, the t-test is still the industry standard, unfortunately, because I think it's actually we've moved beyond. But let's review what we've done so far. We've covered that. Move my YouTube feed. We've covered the different types of t-tests, and we're going to go more deeply today with a lot more examples. Remember that t-test is a test for comparing the mean of something in your sample to either the mean in a different sample or an external standard. You can see on YouTube that I'm doing this. Mean over here, standard over there, right? So we have different kinds of examples here. First, is the mean grade of this class 55%? That's an example of comparing the mean of that sample to an external standard. The external standard is 55%, right? Or is the mean grades of this class and the other stats class the same? Or is among students in this class, is your mean stats mark different or the same from your mean biology mark? Do you see a qualitative difference in those three examples? Especially those last, what's the important distinction between the last two examples? See it? The first one is obviously a case of comparing it to an external standard, and the second two are comparing the means of different samples. But the last one is different from the second one in a very important way. What is that? The same people. It's the same people being measured twice. Right? So those are three important distinctions that determine which formula, which kind of t-test we're going to apply. So here's some more examples. Is the mean grade of class 55%? Well, that's a one-sample t-test. That's when we compare something to an external standard, a one-sample t-test. Are the mean grades of two different classes the same? That's a two-sample t-test, but it's an independent samples t-test because the samples are independent of one another. They're different people. And lastly, a two-sample dependent t-test using the same group tested twice, or a group that is very closely related, like husbands and wives or twins. Those are the classic textbook examples. Now we call that dependent. It's also called a paired samples t-test. So keep in mind that nomenclature exists. So here are the basic steps when doing a t-test, and you repeat these steps over and over again when you're doing the exam or exams. You state your null hypothesis. Remember the null hypothesis? What is a null hypothesis? What exactly am I trying to state in a null hypothesis in general? Yes.
Nothing is happening.
Nothing is happening, exactly. Keep on saying that to yourself. The null hypothesis says nothing is happening. It's a baseline state of affairs. I'm going to show you an example where that's not quite the case, but it is the case. It may not seem that it is the case, though. Then we have to choose which t-test scenario to use. And sometimes I won't tell you which one to use. You've got to figure it out. And remember, if it's an external standard, it's a one sample t-test. For two different samples, then an independent sample t-test. And if the same sample being tested twice, it's a dependent sample t-test. Just throw that through your head. Next, we compute the T statistic. How we compute the T statistic depends on which scenario you have identified. Because we found out there's 6 different formulas to use. You got to choose which one is the right one. You're going to compute your degrees of freedom. How you compute your degrees of freedom, again, depends upon which t-test scenario you chose. So that second step there is quite important. That determines everything. Remember, degrees of freedom is just how many people you have in your sample. It isn't really just that. Think about it that way. So it's the freedom that the variability has to express itself in your universe of sample. That's what it really describes. And there are different formulas for expressing degrees of freedom. But again, it's just a kind of measurement for how many people you have. Right? And last, we're going to use this T statistic that we compute and look up the corresponding value in the back of the book, or if you're not taking an exam, you go online and use a T calculator to figure out what to look up. And when you compare your version to the book's version, you can interpret the outcome. When we interpret the outcome, we can either reject or fail to reject the null, and we answer the question. It's important to always answer the question. Don't just do the math, you answer the question. We're going to go through several examples today. So the p-values. We mentioned p-values a few times, and I want to make sure you get a solid grasp of what we talk about p-values. It is, this definition will freak you out. It's okay. Don't understand it, it's okay. But here's the official definition. The probability of obtaining a result that's at least as extreme as the one that was actually observed, assuming the null is true. What the hell does that mean? Okay. So it's that magical distribution. Remember the null distribution of all the samples from our infinite number of samples, and the p-value is the probability that your sample came from that magical distribution, right? So remember, the test statistic is either the p you're computing or z, whatever it is. So in other words, the probability that what you got came from the universe in which the null is true. That's really what we're testing. Most scientists, believe it or not, do not get this nuance, do not get this philosophical nuance. Many will state incorrectly that the p is the probability of the null being true. It's not true. It's not the case. It's a probability of your sample coming from the universe in which the null is true. If it helps, think of it this way. The probability that the result you computed was due to luck. Okay, so even though now I've given you the theoretical foundation of theoretical universes where your sample came from, you can put that aside and just think about this if this helps you for the rest of your life. P-value is a probability, your result, just luck. Okay, so you want a low probability that it's just luck, but a high probability that what you found actually is meaningful. It's not true. It's not really true. That's what most of us kind of rely upon in the heat of the moment. Okay, the p-value is not this. It's not the probability of the null being true, nor the p-value is not standard type 1 error, and all that other stuff. Okay, so put that in your mind. Just think of this. Think of that. Right? One rejects the null if the p is less than alpha. What is alpha? Remember alpha? What is it? That's what it tends to be. What is it conceptually? What am I measuring with alpha? It's a kind of error. What kind of error is it? You got 2 to choose from. Type 1, exactly. It's the level of acceptability type 1, of acceptable type 1 error in your sample. So if you're saying that my probability of well, let's just not go too deep into the philosophy. You reject your null hypothesis if your computed p-value is less than alpha. Right? So if we decide to test for 95% confidence, our alpha is 0.04. So that's the amount of error in our scenario. So the rest of it is not error. The rest of it is confidence. Right? So we set our alpha at 0.5. We could set our alpha at different numbers. We tend to set it here. And if no one tells you what to set it at, assume it's over there. That's the way that Western science works now. Okay. When we do our test, we compute our p-value. Or you look up in the back of the book what a p-value range is, sometimes what the book gives you. What do you do with it if our p is low lower than the alpha, you reject the null. If the p is higher than the alpha, we don't reject the null. Do I ever accept the null? No, never accept the null. You just fail to reject it. Okay? What do I do if my p-value is equal to alpha? What's 0.5? By convention, we reject it as well. Okay, so summary. So if my p is less than or equal to alpha, we reject the null. If it's greater than alpha, we fail to reject the null. And when we're doing studies in science, we always want to reject the null because that's fun. Finding significance is fun. Rejecting the null is fun. It means you found something new. Right? So when I talk about this, I talk about this as being the good outcome because we want to find new things. Rejecting the null is always exciting, and it means that you found significant results that is publishable and discussable and things like that. Okay? So the old phrase, if p is low, the null must go. Drill that phrase. If p is low, the null must go. Right. Now, I gave you a link here of how to think about the p-value, and the link doesn't work anymore, I discovered. So it doesn't work. But you could just Google understanding the p-value in YouTube, and there are endless videos that attempt to describe what that is. Right. So that helps. If that means anything for you. Now, we have confidence intervals and p-values. We don't report both of them. Choose one. In modern science, we prefer to report confidence intervals, but they tell more or less the same information. The difference is the confidence interval gives us a range in which we think we are confident 95% of the time, and the p-value tells us whether or not we can reject or accept the null. So the p-value is a little more limited in what you can do with it, the amount of information it gives, so we prefer confidence intervals. But we never report both. Well, some people do it wrong. So you see in very low-quality journals, papers report both of them. That's just really evident. Take that out. Right. So if we compute an odds ratio, let's say we're computing a relationship between smoking and lung cancer. Remember odds ratios? Don't forget things we did 2 weeks ago because midterm's coming up. Okay. And we have odds ratio of 6.5. Is that high or low, by the way? Is that a high or low odds ratio? Do you remember the cutoffs? It's a very high odds ratio. Generally, we say anything that's 1.5 or above is high. If it's 2 or above, it's like really notable. 6.5 is a very high odds ratio. It means that there's a strong relationship between smoking and getting lung cancer. So with ratios, what's the magic number that tells us nothing's going on? 1. Exactly. We care about 1. It's different from 1. That's the first observation. How different from 1 is the second thing we care about. So let's say we can get a p-value for an odds ratio. The p-value tells us whether or not I can accept or reject a null hypothesis. So let's say again, here's my odds ratio. I compute a 95% confidence interval, meaning that. How do you interpret that in words? Do you remember this? Yes.
With 95% of that odds ratio falls in the range of 2.57.
Yeah, more or less. Yeah. Or if I did this experiment a billion times, 95% of the time it would fall. I would get a sample that's between that range here. 5% of the time it wouldn't. Okay? So the other way to interpret this is to figure out if the magic number is in that range. What's the magic number for odds ratios? You said it. 1, exactly, because 1 tells us nothing's going on. Is 1 in this range? 1 is not in that range. So we know from interpreting this odds ratio that most of the time I will not get an odds ratio that tells me nothing's going on. So most of the time I can reject a null. By most of the time, 95% of the time, which means significance. So the quick and dirty way of interpreting an odds ratio from a confidence interval is to look for 1 in between them. There's no 1 there. Significance. Okay? If I want to compute a p-value, on the other hand, for the same experiment, what's the null hypothesis that I'm testing for an odds ratio? What do you think? It's on the slides, you see it right away, right? Is I'm testing whether or not the odds ratio is 1. If 1 tells me nothing's going on. The null hypothesis says nothing's going on. The odds ratio says nothing's going on. So my null is odds ratio is 1. There's nothing going on. And let's say I did the math and I got a p-value of 0.001. Is that low or high? It's low. The null is low, so the p is low, so the null must go. So did I reject or fail to reject the null? I reject the null. P is low. The null must go. It's rejected. Okay. So using either the p-value method or the conversible method, I get the same conclusion. I can either look right there and say, hey, 1 is not in that range, therefore the null must go, or I can compute a p-value and compare it to my alpha and say, oh, the null must go. Either way, it gives me the same answer. That's why we don't do both. We choose one. We prefer this one. This is fine. Clear on that? Okay, good. So now let's go back to t-tests. So remember that t-tests come in two types. We talked about the one-sample t-test and two-sample t-test. Clear about that. You know, the two-sample t-test comes in two types as well. Dependent sample, independent sample. Independent is when it's different. Dependent is when we're testing the same people twice, or husband and wives, or twins, or anyone with a systematic relationship to each other. And when we do independent samples, there are also different types. Ones in which the variances of the two groups are the same, or ones in which they're different. So that gives 1, 2, 3, 4, 5 different types of tests we can actually apply. Even though it looks like there's 2, there are 5 different formulas we can apply. So for independent, for independent samples t-test, how do we know whether the variances are the same or different? We have these two here. How can we tell? Last time, we talked about Levine's F-test. I will not ask you to compute Levine's F-test. I will ask you to interpret Levine's F-test. Levine's F-test is a test of whether or not the variances of my two samples are the same or not. Okay? And when I say the same or different, I mean statistically the same or different. Every year, there's always one person who looks at the actual variances. Oh, they're different. They're not statistically different. You have to look at the ranges to figure that out. Okay? Levine's F-test has its own null hypothesis. What do you think the null hypothesis is if I'm trying to determine if the variances between two different groups are the same or different? What's the null going to be? Just encourage. Go ahead. Take a shot at it. It's on the slide anyway. It's really they're the same. All the variances are the same, right? So the null of the original question is the means are the same. The null of Levine's F-test, the variances are the same, right? So this is separate from that. We do this in order to do that. Okay? So the null hypothesis of Levine's F-test, the variance of sample 1 is the same as the variance of sample 2. That's what we're testing with the F-test. If I run an independent samples t-test, SPSS will give me Levine's F-test output so I can make a decision about which path to take. Let's say it gives me a p-value for Levine's F-test of that. Is that low or high? That number. That's a low number. It's much lower than 0.05. So what do I do with this null? Do I reject it or do I fail to reject it? I reject it. If the null, if the p is low, the null must go. Okay? So if I reject this, are the variances the same or different? They're different. This one says the same. If I reject it, it means they're different. So I know to use the t-test formula for different variances, unequal variances. Straightforward. I know I'm talking slowly about it and being condescending about it. You got to get it straight. There's always someone who thinks they understand, not paying attention. Drives me nuts. So what I expect from you to do is I want you to know how to compute a one-sample t-test. We're going to do that today. I want you to know how to compute a two-sample dependent samples t-test. We did that last time. We're going to do it again today. And I want you to know how to interpret the SPSS output for all of them. I won't ask you to compute a t-test for a independent samples t-test. It's just too complicated. There's a requirement for that. Just these two. The only math you need to know, but the rest I need you to understand. The interpretation, the process into it. I will ask you to compute a 95% confidence interval as well. I give you this information. Remember the standard error of the difference? What is that? Standard error of the difference. Remember that? Next is what does it describe? Where do I get it? All right, let's go back in. Remember the magical theoretical distributions. Okay, so if I'm taking, let's say I'm trying to compare whether or not the ages of this class and the other stats class are the same, right? So I'm taking, I can take you from the universe of stat students. I can take the other class from the universe of stat students, compute the differences in means, put that aside. I can take another 2 samples from the universe of stat students, compute the differences in their ages, and put it over here, and do it again a billion times. So I have a bunch of differences in ages. And if I do a frequency distribution of all those differences in ages, most of them will be somewhere in the middle over here, a difference of, I don't know, 1 or 2 years. Some fewer will be a difference of, I don't know, 1.5 or 2 years, and so forth, until I get this magical, again, normal distribution showing the frequency distribution of all the differences in mean ages of all this infinite number of stat students selected at random. The standard deviation of that magical, non-existent theoretical curve is the standard error of the difference. Okay. The same way, if I was computing just mean IQs, let's say, and I was choosing just a billion different samples of students at computing a mean IQs, I can plot a distribution of all the possible IQs I could get. It will be shaped like this, and the standard deviation of that curve would be the standard error of the mean. These are theoretical things, theoretical constructs. They don't really exist. So I estimate them. I estimate them using the standard deviation of who I have. I have you. So take your standard deviation. All right. So theoretically, get that in your head. This is a theoretical construct that I estimate using my sample. Degrees of freedom is a measurement of, again, how many people I have. Okay. Now to remember, we call t-tests and z-tests parametric tests. You'll hear this a lot in future classes, parametric tests versus non-parametric tests. It's not that important to get it straight in your head, but it's useful. So a parametric test likely seeks to estimate a parameter and relates us to a magical theoretical distribution. All the stuff you're hearing about by now. Right? That's what a parametric test means. We will do non-parametric tests later, like a chi-square or a correlation coefficient. Those are non-parametric tests. They're not attempting to estimate something in a magical population or whatever. That's what that means. So in most parametric tests, we always look something up in the back of the book. There's z-scores, t-scores, and future tests will look up things as well. So it's easy to get confused about how to read those tables. So get some practice in there. You know, on an exam, I will give you the table to look up. You've got to compute the requirements, the characteristics to find the right thing on the table. So for the t-tables, you need to know the following information. You need to know degrees of freedom. And this is how you do it. For the one sample t-test, your degrees of freedom is the number of people you have minus 1. For the two sample t-test, depending upon if it's independent or dependent, get that straight. Dependent means the same people being tested, or husbands and wives or twins. Independent means different people being tested. If it's independent, you add everybody up and you minus 2. If it's dependent, you care about the pairs of people you have, minus 1. Okay? You need to know your alpha level. Unless I tell otherwise, it's always 0.05. It's not just my rule, that's the way it works in science in general. It's always 0.05. The next popular one is 0.01. And there's no reason for that. In fact, there is a huge statistical papers written about the history of science asking, why is it 0.05? There's no actual reason for it, except I got 5 fingers. So 5 is a magical number. We could have chosen 3. We chose 5. Okay? We need to know whether it's a two-tailed or one-tailed test. It's always going to be two-tailed. Let's say otherwise. And really, experts decide which one to use. So in this class, when it's a t-test, it's always going to be a two-tailed test. But recognize that out in the wild, some people will start to apply one-tailed tests. And the difference, again, between one-tailed and two-tailed tests is one-tailed implies the knowledge of the direction that you're testing. And two-tailed says, I don't care about the direction. All I care is, are they different? I don't care which one's higher or lower, except they're different. That's the difference. Okay. When you look up this t-value that you're going to compute in the back of the book, what do you do with it? Well, the one that you compute is your t. The one that the table has is the table t. If the table t is bigger, you fail to reject the null. If yours is bigger, you reject the null. So I always said we always like to reject the null, and that tells us that we're special. tells us that our science is finding something interesting, right? So we like to be big. So if yours is big, then your science is big. Found something big. That's why I remember it. There it is. Okay, first example. Are we clear on the specifics? That summarizes it fairly well. Okay, we're going to visit 2 different public schools in Ottawa, and we're going to see who's being held after class in detention, right? And we're going to compute whether or not the ages of the detention students in this school are different from the ages of detention students in that school. What kind of t-test is this? Is it one sample? It's 2 samples. Okay. Is it independent or dependent? Someone take a shot. Yes, ma'am. Exactly. We have 2 different groups of students here. They're not the same student. Right on. So we know what to do here. Okay. Oh, there it is. It's on the slide. So you already. So independent samples t-test. Here is our data is plural. Right. So school 1, 2, 3, 4, 5, 6, 10 students here, 10 students there, about 20 students in total. Are their ages. Okay. What's the null hypothesis going to be? We always start with our null hypothesis. The null always says that nothing's going on. So it's going to be that the mean of this one is the same as the mean as that one. I could have written mu there instead of m. M means my sample mean. Mu means population mean. It's a philosophical choice, which one you prefer. I'm not going to be picky about which one it is. Okay. So that's a no. The alternative is going to be that they're not the same. Why didn't I choose to put a less than or greater than sign here? Yes. It's a two-tailed test, exactly. If I had a less than sign here or a greater than sign, it implies that I care about the direction. I don't care about the direction. If I cared about the direction, I'd have to do a two-tailed test. Oh, a one-tailed test, rather. We're not doing that. We're doing two-tailed tests only. All right. We have our null. Excellent. Next, we have to check our assumptions. Remember the assumptions. We didn't spend a lot of time on that. Let's go through those. All observations must be independent of each other. What does that mean? It means that the first student in detention, his age is this. Does that have any bearing what the age of the next student is going to be? It shouldn't. It's not like, hey, you're 12 years old, I need another 12-year-old next year. Makes sense. So assume that they're independent unless there's a reason to assume otherwise. So the study design tells if it's independent or not. And really, I'm not going to be that tricky with you in a stats class. Right? So let's assume they're independent. Next. The dependent variable must be measured on an interval or ratio scale. What is the dependent variable in the study? I'm looking at the mean ages between the different schools. What is the dependent variable? We've got 2 choices. Guys are making me worry. Yes, you answered all the questions. That's the independent one. No, that's right. All right. What are 2 variables in this study, first of all? Age is obviously one of them, and the other one is what? The school you're in. Okay, 2 choices. Which one is the dependent one? Whisper. Yes, ma'am?
The school affects the ages
That's a research question. So which is the dependent variable? The dependent variable is the one that changes in response to the other one. Well, the giveaway here is that the dependent variable must be an interval ratio scale. Of the 2 options, only one of them is on the interval ratio scale. It's the age, obviously. Okay? That means the independent one is going to be what school you're in. Okay? So get them straight in your head. Okay, the dependent variable must be normally distributed. How do we know that? Well, we don't know that. We know, just by common sense, that age does have a normal distribution. But we don't know for sure. So we're going to do in a second something called the Kolmogorov-Smirnov Test, a test for that. If we can't do that test, we can assume normality. We usually assume normality if we have 40 people in our sample. 40 is kind of the cutoff. Right? Sometimes we can't assume normality and we just go for it anyway. All right. The last thing we do is we check to see if the variances are equal. And what test do we use for that? We use Levine's F test. Okay, so we got all this stuff going on here. The 2 scary things are these 2 things. Yeah? The Kolmogorov-Smirnov test and Levine's F test. Let's see how it plays out. And by the way, this is an independent samples t-test, right? This is not one in which I will ask you to compute the t-value. This is one in which I'll ask you to interpret the value. I only ask you to compute the T statistic for the one sample and the dependent samples. So let's work it through. What is this Kolmogorov-Smirnov test? This is a test to see if my data is normally distributed. Why does that matter? It matters because the T test doesn't really work that well unless it's normally distributed, right? So the Kolmogorov-Smirnov test has its own null hypothesis, and this is what it is. The data should be R. The data are normally distributed. Okay. Now I mentioned the null hypothesis, it always says nothing's going on. Well, that kind of says something's going on, right? So that's what I was talking about when I was saying it's kind of tricky, this one. So think about normality as the default state, as the boring state. So the null here says the boring state is true, right? Everything's normally distributed. That's great. So if I end up computing a p-value for the Kolmogorov-Smirnov test that is very low, let's say lower than 0.05, what do you think that means in terms of normality for my data? Are my data normal or not? P-value is very, very low for the Smirnov-Kolmogorov test. It's not. If the P is low, the null must go. If that's my null, the null goes. It means the data are not normally distributed. So that means for this test, I want to fail this test. I want my p-value to be high for this test. Okay? If my p-value is high, I can retain or fail to reject this null. And that's good. Write that down. The Kolmogorov-Smirnov test, you want a high p-value. So SPSS gives you this output for the Kolmogorov-Smirnov test. Actually gives you several tests of normality, pure looks as well, and so forth. Just focus on this one, right? So this is your p-value. Sig is your p-value for SPSS. Sig stands for significance level. That's what p-value is. 0.2 is high. 0.2 is much higher than 0.05. That's good. That allows us to fail to reject this null hypothesis. Okay? Thus, we can assume that our data are normal. So on a test, I would give you this output or the data from the Kolmogorov-Smirnov test and ask you to interpret it. The kind of thing that I would do. So the next thing we do is you have a test for equal variance. So again, that's Levine's F test. Levine's F test has its own normal, its own null hypothesis, and it's this: that the standard deviation for the first school is the same as the second school. Do I want to fail or pass this test? Do I want my p-value to be low or high? It doesn't matter, because regardless of what the outcome is, there's going to be two different t-test formulas to use. This test just tells us which one to use. Right? So here's SPSS's output. Levine's F test gives me a p-value of 0.512. What do I do with that p-value? Do I retain or reject this null hypothesis? Is that low or high? Someone be courageous. Give you a chance. So it's high. So if it's high, do I reject or fail to reject this? I fail to reject it. The null is not low. No, the p is not low. Therefore, the null does not go. Right? What do I do? Well, what I can do is I know to use equal variance formula. SPSS will give me two outputs. One assuming equal variances and one assuming not equal variances. This value tells me which one to use. Because I did not reject this null, I know to use the equal variances output. Right? So next thing, we have to compute the T statistic. Again, this is an example of the independent samples t-test. I do not ask you to do this math. Instead, I give you the SPSS output. And here is the SPSS output for this particular test. Remember, SPSS gives us a scenario in which equal variances are assumed and a scenario in which equal variances are not assumed. We just said that our p-value for Levine's test was high, therefore equal variances are assumed. We use this first row here. Let's go through what all this means now. Using this option, this is our degrees of freedom. 18. Not surprising. We had 20 people total. We subtracted 2, we got 18. This is the p-value of this scenario. Notice the p-value is different in that scenario. So depending upon which of these assumptions I made, it gives me a different p-value. This is what I care about. Is that low or high? If my cutoff at 0.05. It's low. It's lower than 0.05. So automatically, you know to do what with the big null hypothesis. I'm going to reject that null hypothesis, which is great, because it means you found a difference. It means that the two means are not the same. That's great. Now the rest of this is interesting. The rest of this data won't mean a lot to you, but actually it's useful. So this is the mean difference, meaning that on average the differences in ages between the two of them. The standard error difference, that standard deviation of that magical curve I talked about, they've estimated here for us. And this is the 95% confidence interval of that. You can compute this yourself, as we will in a moment. Okay. But we know now the p-value is low, therefore we can reject the null and answer the question. Okay. We answer the question, by the way. The original question was, are the mean ages same or different? The answer is, they're different. Okay, good. Now, let's say you have to compute your own 95% confidence interval. SPSS didn't do it for you. You need to know the mean difference plus or minus the T statistic times this magical thing here we talked about. Okay? So I'll give you a lot of this information. I may not give you this stuff. I figure that out. You also need to know your degrees of freedom in order to look this. Let's break it down. We know that the mean difference was minus 3.6. We know that from the SPSS output. This we have to look up now. We know this from the SPSS output as well. That we look up on page 412, given our degrees of freedom, and we get that number, 2.1. Do the math, we get that. You'll notice that is slightly different from the numbers here. Slightly different. Okay? And the reason they're slightly different is that SPSS uses a slightly different table lookup than the back of your book does. Because the one in the back of your book has a lot of summaries, rounding up and rounding down, stuff like that. Okay, so don't be too concerned when you get a slightly different number from the computer output. Computers all do things slightly differently, but they're more or less the same. So this is the mean difference in ages between the two groups, and this is what the mean probably is, the range of what the mean is with 95% confidence. All right. That's an example of the independent sample t-test. Let's work through another example now. In the United States, mothers who live in poverty generally have babies with lower birth weight than those who do not live in poverty. The average birth weight for babies is this number, 3,300 grams, and the average birth weight for women living in poverty is 2,800 grams. Okay? Impoverished group, non-impoverished group. We find that babies born to 25 women in a certain program weigh this amount, and that's the standard deviation. Has this program been effective at improving the birth weights of babies born to poor women? Now, that's a long question. A lot of numbers there. You've got to figure out, what are they asking? And what test can I apply to answer the question? What do you think? What kind of test is this? It's obviously a t-test. Which one is it? It's a lot of, this is a classic question to just the distraction purposes. One sample dependent. That doesn't exist. It's not two sample dependent, no. Yes. Why is it a one sample? It is one sample. Why is that? Okay. Yes, it's a one sample because you only have one sample. This is what you have. You got this point here. That's the one sample you have. Okay? All this other stuff is distraction. Now, in a one-sample t-test, you're comparing your sample to an external standard. What's the external standard here? You got two choices, either that or that. That is a distraction. It's this. Because we're looking to see, is my sample, in which I have a special program, is it making my baby's birth weights different from the American average? was not in poverty. Okay, so let's work it through. It's one sample t-test. The null is going to be, is my sample different from 2800? Or the same, is my sample the same as 2800? I can write that like this, confuse you. The mean minus 2800 is 0, same as saying the mean is 2800. Okay? The trick here is finding which numbers you care about. Now, this is a bit misleading because the question is actually asking, have we improved our scenario? Right? So there's directionality implied here. But I told you that we don't test for direction in this class. So it's going to be a two-tailed test. Let's see how that works. This is actually the easiest kind to do. The one sample is so freaking easy. So it shouldn't make you upset. Right? We're going to compute T statistic. This is the formula for T statistic. It's our number minus the external standard divided by this thing that's called the standard error of mean, which again is standard deviation of a magical theoretical construct. Okay, how do I compute this magical theoretical standard deviation? I estimate it from a sample. In my sample, I have a standard deviation of 500. I divide that by the square root of my sample, which is 5. Like that. Right? So you did that formula a while back. I compute my SEM from the standard deviation in my sample. So this is what my SEM will look like. I plug it into my formula, and I get all of that. A t-value of 2.75. Look at these split, very fast, simple, no issues there. Very straightforward. Okay. What do I do with this number now? Exactly. I compare it to the thing in the back of the table, right? So we're going to look up the back of the table. Our degrees of freedom is this. Number of people, -1, so 24. My alpha value is 0.05. And I load page 412, and I look up 2.06. Now, what do I do with that? Our number is bigger than the table's number. Therefore, what do I do with the null? Reject or fail to reject? Reject. We said like our number to be bigger, right? Now, at this point, hopefully you're asking, I have to ask the question too, but the program was a success. Right? Now, the program could have had like birth weights that were really, really low, and I get the same result, I get a result that my t-test tells me that the means are different. But I'm eyeballing this and saying, well, my number is actually bigger than 2,800, therefore it's a success. Right? So sometimes you're in negative numbers for t-values. What do you do with those? Take the absolute value. So it comes down to it. I'll go over that in a second. But we're also going to look at computing. I will never ask you to compute a confidence interval for a one-sample t-test. And the reason for that is the math is horrendously complicated. And you get these skewed values, and you don't need, doesn't really teach you much about that. So this class, we will not compute 95% confidence intervals for one-sample t-test. We will do it for two-sample t-tests, not one-sample t-test. Right? If you want to look at what that looks like, you can go online and look at the t-test calculator. Right, another example. 4 pairs of husbands and wives. Husbands and wives. Automatically, what kind of test is it going to be? Two-sample, dependent, paired samples, obviously. See the word twins, husband and wives, multiple testing, it's always going to be dependent samples. So 4 pairs are asked to rate on a scale of 1 to 10 how well their marriages are going. This will end well. Okay? And you want to know whether their husbands and weight of their relationships and wives. Great. So, D7 that's fantastic. And this is your null hypothesis. As long as I get that straight in your head. You're saying that the mean husband rating is the same as the mean wife rating. Nothing's going on. Of course, deep down, we want them to be different because that's fun, right? That's fun science. That's why I reject this null if you can. Say, yeah, we found something cool. Make people upset. Okay? So this is our null. Let's begin. This is one of the ones we will be computing it. So the first thing we do is we set up this spreadsheet, a table of some kind. Here are the couples. Here are the husband's rating and the woman's rating. So couple number 1, the husband thought they were great. The wife, not so much. Couple number 2, the husband's rating, we're okay. The wife, oh, we're great. Couple number 3, the husband said, hey, we're doing really well. The wife said, we're doing really, really well. And this one was opposite. Okay, so you see there's going to be some variation here. What do I do with all this? Well, like we did last time, I just compute the differences and the differences squared, add them all up. Okay. So 0 is the sum of my differences, and 10 is the sum of my squared differences. Not the square of the sum of differences, the sum of my squared differences. The difference? Yeah, good. Right. And I plug it into this magical, obnoxious knowing formula, which again, you will not be required to memorize. Okay? And I get 0. Well, that's interesting. A t-value of 0 is fine. We can do the same thing like we did last time. Now, as I said, if my t is negative, don't worry about it. Just take the absolute value. So if the absolute value of my computed t is bigger than my table, I reject. If the absolute value of my computed t is less than my table, I fail to reject. Right? Straightforward. So I look up in the back of the book the value here. I know my alpha is 5, my degrees of freedom is 3, so that's my t from the back of the book. I compute 0. It's less than back of the book. Therefore, what? What do I do with my null? My t is not bigger than the back of the book. Yes? I fail to reject my null. Exactly. Right? So unfortunately, the husbands and wives actually are saying the same thing. That's no fun at all. Okay? So 3 straightforward examples, and that's as hard as it gets, really. So try your homework and see what you think. Yeah, we're done? Well, cool. Yeah. Quick and dirty.